So far, you've encountered data frames in conjunction with truth tables, but it turns out they're important far more generally. A data frame is the most important type of structure that you'll be working with when you do data analysis in R. There are 100 or so data sets available as part of standard R, and I have loaded a particularly simple one named trees, and I've written a little shiny app that displays it. You can see that it consists of 3 columns named girth, height, and column that give the diameter, height, and an estimate of the volume in some unit for a number of trees. Each row refers to an individual tree, and the only reason I wrote a shiny app to display this is it does a rather pretty job of typesetting the free columns. So far, I would say the most difficult aspect of working with R Markdown is using this table of contents. Here we go. So now let's explore trees. What is it? It's a list of columns. Each column is a vector, and since a data frame, like a matrix, has rows and columns, to a certain extent you can treat a data frame like a matrix. I'd say the two most important differences are all the columns in the matrix are of the same type. They're usually numeric vectors. The columns in a data frame can be of different types, and that's because we're not making a vector of vectors, we are making a list of vectors. And in R, a list can include objects of any type you like. An easy way to get a quick glance at a data frame is to call the function head. And so if I ask for head of trees, I'll see the girth, height, and volume for the first 6 trees. If I want to specify an individual column by name, I use a $sign. So trees $volume is just a long vector, volume of the first tree, volume of the second tree, and so on. If I want only a subset of the columns, I do exactly what I would do with a matrix. Here I want a selection of columns, but I want all the rows. Since the index in front of the comma is the row index, I leave that blank and I say, as my second index, I want just the girth column and the volume column. If I happen to know that those are the first and third columns respectively, I can get exactly the same effect by including a vector consisting of 1 and 3 after the comma. If I want a single row, since the first row is the row index, I say I want row 5 and I want all the columns, and you see I get a vector whose 3 components are numbers and they have names, girth, height, and volume, which might be useful. I can treat it as a vector, ask what's max, I will get the largest of those 3 numbers. Suppose I want a range of rows. That's perfectly easy to do. I just say I'd like rows 1 through 10, all the columns. There I've got it, the first 10 rows out of my database. If I want to select a range of rows by imposing a condition, I use the function subset. So I say I want a subset of the data frame trees with the rows selected by the condition that the height has to be greater than 75. And when I display that, you can see, indeed, I'm getting all the rows with a height greater than 75. If I want to select not only by row, but also by column, I can do that. It takes me a while always to remember the syntax. The third argument now is select equals. So the second argument is a condition that selects the rows. Height is greater than 75. And in the third argument, I say I want to select only the height column and the volume column. This is going to turn out to be very convenient for you. If you encounter a database that has more rows and more columns than you'd like to deal with initially, you can build a subset of it, get everything working, and then maybe go back and deal with the entire data set. Now, your knowledge of logical operators is going to start paying off. Because when I apply a mathematical operation like is equal to, is less than, is greater than, to a pair of numerical vectors, I create a vector of the same length where the logical operation operates component by component to produce a logical vector whose components are each either true or false. If I have multiple logical vectors, I can now apply logical operators to them, and they operate component by component to produce a new logical vector. Only remember, use single ampersand for and, use single vertical bar for or. So let's try this out on our trees. Let's make a new vector named isBig, and this is going to be the result of taking the logical and of girth greater than 12 and height greater than 75. So this will give me a vector where each component is true if both these conditions are met, false if either of them is not met. If I look at the head of isBig, it starts with lots of falses because the small trees are earlier in the database. I can do a lot of arithmetic by simply exploiting the fact that true gets converted to 1. If I take the sum of this, that's the sum of all the trues in the vector, it will give me 11. That's precisely how many trees meet this criterion. If I want to figure out which trees they are, I use the R function which. That gives me a vector of indices for the rows that meet the criterion. So the big trees are in rows 17, 18, 21, and so on. And I can confirm that by asking for trees with row numbers. Notice there's a blank entry after the comma, so I'm selecting rows. I'm selecting the ones for which my criterion is met, and there they are. Of course, I already told you an easier way of doing this. I can form a subset of trees for the criterion of big diameter and big height. From time to time, however, it's useful to have this list of indices, particularly if you want the trees that don't meet that criterion. It gets a bit tedious using trees, $, girth, and so on. You can get around that by using the function attach. If I say attach trees, that means girth means trees, $, girth, etc. And if I want, for example, to find the index numbers for all the trees where the diameter is equal to the smallest diameter encountered, or the height is equal to the smallest height of any tree, or the volume is equal to the minimum volume of any tree, then when I select those rows, I get just two trees. Number 1, I believe, has the tree with the smallest girth. Number 3 is the tree with both the smallest height and the smallest volume. And you can visualize that you can put arbitrarily complicated logical expressions in here to do your selection. Whenever you do an attach, do a detach at the first opportunity. Otherwise, you will discover 6 files in the future that suddenly height is being misinterpreted as a column in this particular data frame. What about a data frame with factor columns, ones that are non-numerical? Well, let's bring in some new data sets. I was delighted to discover that all the data sets that are mentioned in Chihara and Hesterberg's Mathematical Statistics textbook, which is one of the references for this course, are now available as an R package, so you don't have to load them from files. All you have to do is to install the package resample data, then call library resample data, and until you reinitialize R, all of these packages are in the set of data sets that R has put at your fingertips. In the scripts I wrote, either I didn't know that this had been done or it hadn't yet been done, so I tend to load them from files, but this is much easier. One of their data sets is the General Social Survey from 2006, and I've chosen this because it's a data frame that has no numeric columns whatever. It does have a lot of columns, though. These surveys are carried out either every 2 or every 4 years, and people answer literally hundreds of questions, and it's all tallied. You find out where they live, male or female, level of education, marital status, religion, and so on. And notice, in order to list all these columns, I have to spill over to a third row. For each of these, I can find out the possible factors and their frequency of recurrence by asking for a table. So when I ask for a table on the region column, it gives me the names of all the regions and the number of participants in the survey from each of them. I can do the same thing for politics. And if I want to have a more picturesque way of looking at these, I ask for a bar plot instead. Some of the region names are too long and get wiped out, but you can see the height of the bars indicates the number of people in each region. If I do the same thing, I find out that there are lots more moderates than the various flavors of liberal and conservative. Life gets interesting now when we have 2 factors. If we have 2 factors, we can say table, give it the first factor, give it the second factor, and now we get a table that shows us the number of conservatives in the mid-Atlantic, the number of extremely liberals in the South Atlantic state, and so on. And if I want to form a subset of this big data set, I can fairly easily do that by saying I want a subset of this data frame, selecting rows by the criterion region equals mountain and politics equals liberal. It took me a while to remember I need quotes around the name of the factor, but I don't need quotes around the name of the column. And in order to narrow down this data set, I said I only want to look at the religion, income, and who they voted for president in 2004 column. So I now get a much more manageable data set. There are its first 6 rows. Suppose we mix the two. We can do that because a data frame is not a vector, it is a list. And the data frame I'm going to use and as an example is one that gives statistics on all the babies born, I'm not sure they're all, on a large number of babies born in North Carolina in 2004 with information about the gender of the baby, the weight, I assume that's in grams, so as a physicist I object, the mass in grams of the baby, the number of weeks of gestation, a redundant column specifying whether the mother uses tobacco, and a column specifying whether the mother uses alcohol. Let's immediately attach this data frame because this is a rather long name to type in, and R is just full of functions for analyzing a numeric column like weight. I can ask, for example, for the median. I can ask for the mean and discover that the mean is slightly larger than the median. I can ask for the maximum weight. This is a real baby Huey, 5,131 grams. If I want to picture the whole thing, I ask for a histogram. By setting breaks equals 20, I get 20 bars in my histogram. And you say, hey, that looks an awful lot like the grade distribution on the life sciences midterm. Why is that so? Well, I'm told by someone who's a bit knowledgeable on this subject that there's a theory that these statistics that are biologically determined are the result of a lot of different genetic factors being combined together, some of which might tend to increase the birth weight, some of which might tend to decrease them. And when we get to the central limit theorem much later in the course, you will learn that under those circumstances, the histogram tends to look like the classic bell curve. If I want a compendium of results on weight, I call the function summary. That gives me the smallest weight, the largest weight, the median and mean weight, and the first and third quantiles. A quarter of the babies had less mass than this, a quarter had more mass than that. And if I want to display this graphically, I call the box plot function. There's the median, there's the first quartile, there's the last quartile. I believe these bars are drawn 1.5 times this separation out from the two quartiles. And this is a reasonable criterion for saying anything beyond this you can call an outlier. So these are a number of exceedingly massive babies. Here are a number of low mass babies. There are factor columns here too. You'll notice they turned the mother's age into a factor by doing 5-year groupings. Here's a bar plot of it. And now comes the interesting part. The folks that wrote box plot allowed it to take a so-called formula as its argument. And this says, show me box plots that indicate how weight depends on gender. And what it does is show me the box plot for the weight of the female babies and for the male babies. And you say, aha, male babies are heavier on the average. But is that statistically significant, or is that an artifact of the fact that we were just dealing with a couple of thousand births? That's the sort of question we will be addressing throughout this course, and I'm not going to try to give you an answer today, except in one very specific case. Here's another one. Gestation time as a function of alcohol usage. And you say, ah, I knew it. The mothers who drank tended to have their babies earlier. Mothers are warned about this. I think I looked and discovered there were only 3 mothers in the survey that admitted to using alcohol. So this is probably a totally meaningless result. What about weight as a function of mother's age? Well, it does look as though for mothers in their late 20s and early 30s, the average birth weight is higher, that young mothers tend to have lighter babies, and if you are into this sort of thing, there might be a lot to be learned from this database. I find it kind of interesting that most of the interesting substantive questions raised by this data analysis have nothing whatever to do with the subject matter of mathematics. Well, I've run to 20 minutes. I think I'm going to end this video and start a new one to finish things up. But my goal in doing these videos was to find out how the timing went, so that's just fine.